Let's now understand the concept of molecularity of a reaction. A balanced chemical reaction doesn't explain the mechanism of the reaction. That is, it doesn't explain how the reaction takes place. A reaction may take place in a single step, called an elementary reaction, or in multiple steps, called a complex reaction. Each step in a complex reaction is called an elementary reaction. The sequential representation of all the elementary reactions in an overall reaction is called the mechanism of the reaction. The number of reacting species, such as molecules, atoms, or ions, of an elementary reaction, which collide with each other to bring about a chemical reaction, that is, to form a product or products, is called the molecularity of that reaction. Molecularity of a reaction is the property that helps us understand the mechanism of a reaction. A reaction in which only one molecule takes part is known as a unimolecular reaction. For example, the decomposition of ammonium nitrite. Bimolecular reactions involve two molecules. For example, the decomposition of nitrogen dioxide. Trimolecular reactions involve three molecules. For example, the combustion of nitric oxide. Why are the reactions involving more than three molecules very rare? Now let us understand how the collision theory explains the reactions which involve more than three molecules. Collision theory states that as the number of reacting species or molecules increases, the probability of simultaneous collision of reacting molecules decreases. Therefore, the possibility of simultaneous collisions between four molecules is much less than the possibility of simultaneous collisions between three molecules. Hence, reactions involving more than three molecules are very rare. Therefore, the molecularity of a reaction cannot be more than three. Reactions involving more than three molecules take place in several steps, and such reactions are called complex reactions. Note that the molecularity of a reaction that takes place in a single step is equal to the total number of reactant molecules involved in the balanced chemical reaction. Let us now move on to the mechanism of a complex reaction involving more than three molecules. Consider the reaction of hydrogen bromide with oxygen. Here, four molecules of hydrogen bromide react with one molecule of oxygen. These molecules must collide simultaneously to react, but it is highly unlikely that five molecules would collide at the same time. Therefore, this reaction takes place in several steps, as shown here. You can clearly see that each step involves two molecules. That is, the reaction is bimolecular. Hence, when a reaction involves more than one step, its molecularity depends on the elementary steps. From this, we can conclude that complex reactions involving more than three molecules generally occur in more than one step. When a reaction involves more than one step, the elementary step that can proceed no faster than any other step is called the slowest step. The slowest step of the reaction is therefore called the rate-determining step. This concept can be understood better by drawing an analogy with the preparation of a cake. The three major steps involved are preparing the dough, baking, icing. You can make dough for 50 cakes. However, only 20 cakes can be baked at a time. Hence, the number of cakes on which you can put icing will depend upon the second step, baking. Therefore, baking is the rate-determining step here. Let's now go back to the reaction of hydrogen bromide with oxygen. In this example, steps 2, 3, and 4 are very fast and take less than a minute. However, step 1 can take up to a year. Therefore, step 1 is the rate-determining step for this reaction. For this step, the order and molecularity of the reaction are the same, 2. Thus, for a complex reaction, the order is given by the slowest step, and in general, the molecularity and order for the slowest step always remain the same.